Okay, so this is all about special angle pairs, and already we've defined linear pair, which are the yellow and the blue sitting on a line like this, and the linear pair postulate, which says they're supplementary and they add up to 180 degrees. A little note about supplementary. The only thing that the definition of supplementary says is that two angles have to add up to 180 degrees. So if you draw a picture, a diagram of a 10-degree angle on your paper, and down the hall in room 340, another student has a picture on their paper and it's 170 degrees, are the two angles supplementary? The only thing that the definition says is that they have to add up to 180. You have a 10-degree angle, the person down the hall has a 170-degree angle. Are they supplementary? Yes. They're not near each other, they're not even on the same paper, they are still supplementary. Do they form a linear pair? No. Okay? A linear pair are a pair of adjacent angles. They have to literally be sharing a side, which implies that they have to be drawn on the same piece of paper, right? Literally stuck together. That's a linear pair. So even though all linear pairs are supplementary, does that mean all supplementary angles are linear pairs? No. Okay? So it's not like one term can be replaced with the other term. They're not the same thing. It's just that all linear pairs, in order to be a linear pair, it turns out that they're all going to be supplementary. Okay? Okay, from our diagram, examples of a linear pair. Angle 1, here's angle 1, and angle what would form a linear pair? 3. Good. Angle 1 and angle 3 form a linear pair because here's angle 1 and we need angle 3 next to it to be sitting on this line and form this straight angle. Okay? So that's by definition. We recognize 1 and 3 form a linear pair. The equation that we could write then is the measure of angle 1 plus the measure of angle 3 equals 180 degrees because of the linear pair postulate, which tells us that they're always going to add up to 180. Okay, so this is going to translate into similar types of problems like you did with your angle addition postulate. But this time, our reason is going to be linear pair postulate. Because we have a diagram here that shows a linear pair. Angle 1 and angle 2 form a linear pair. Yes? Okay. So, like we said before, most important thing, label your diagram. So, measure of angle ABD is 20x plus 2. Here's ABD. We're going to label it 20x plus 2. Measure of angle DBC. D to B to C is this angle right here. And that's 30x minus 22. So we're going to label that in our diagram as well. Now we're going to write our equation. What equation could we write? Now this is really similar to the angle addition postulate, but angle addition postulate you needed 3 statements, 3 given information statements, because you needed one little angle plus the other little angle equaled the whole angle. Here we don't need another one because we already know what it adds up to. Yep. Perfect. this angle now, angle 1, 20x plus 2, plus this other angle, angle 2, 30x minus 22, forms a linear pair, so we know they have to add up to 180. Now we're just going to solve for x. Again, we have this is our equal sign. So you want to, everything on the left, just combine like terms, etc. So we're going to get 20x and 30x is 50x. Negative 22 plus 2 is negative 20 equals 180. Add 20 to both sides. 50x equals 200. Sorry? X is 4. Perfect. So this reason blank here, that reason is always going to either be a postulate, a theorem, sometimes a definition, but this time it's our postulate. Postulate that we applied here to be able to say these two angles add up to 180 is the linear pair postulate. Okay, now if they asked us, all right, now that we know x is 4, what's the measure of angle ABD? What are we going to do? Well, we know ABD is 20x plus 2. So how are we going to figure out what that measure is? Yep, plug in 4 for x. 20 times 4 plus 2, 82 degrees. And then do the same thing with DBC. Now, what should be true about 82 plus 98? They should equal 180. All right, so you guys try this one. I want you to do it all on your own. Label the diagram. Don't skip that step. I know it might seem like you don't need to for this one, but we're trying to form good habits here. So label the diagram, write the equation, put your reason, solve for x. We'll check it in a second. Okay, so you guys did a good job. Remember that you have to have an equal sign to be able to solve. In this case, they didn't give it as given information because we were supposed to just be able to tell that from the picture that it adds up to 180. So solve, you get x is 12, plug 12 back in, you get 64 and 116. Notice that, you know, the diagram isn't really drawn to scale, and that's okay. Don't let that freak you out if it comes out like, wait a minute, it's supposed to be obtuse. I'll try to be better at that, but this one came out, you know, kind of messed up. Okay, any questions on that? Yep. Yep. Okay, so the second pair of, special pair of angles are going to be the vertical angles that we saw in our original discussion here. The vertical angles are these angles that are across from each other in this diagram. So we're going to define those as a pair of angles formed by two intersecting lines that have the same vertex but are not adjacent. So they're not next door neighbors, they are across from each other. They have the same vertex, but they split off into the opposite directions. And again, the definition sort of describes what it looks like, how to recognize them in a diagram. And the theorem is going to give a special property that is always true about that type of angle. So vertical angles theorem says that if two angles are vertical angles, then they are congruent. What does congruent mean again? Yep, equal measures. Sometimes that's shortened to just say all vertical angles are congruent. So our diagram's a little bit more complex than just the two intersecting lines. There's an extra ray thrown in there. But let's see if we can identify what would be a vertical angle to angle 1. Yep, 4. Because angle 1 is formed by this line and this line, right? Here's angle 1 here. It's formed by those two lines. So when you extend those lines, the angle that's formed on the other side is angle 4. So the congruent statement you could write would be angle 1 is congruent to angle 4. You guys recognize that symbol as a congruent symbol? You've seen that before? Yes or no? Yes? So equal sign with a little squiggle over it, that's a congruent sign. 1 is congruent to 4. If we have that as a statement, our reason would be the vertical angles theorem, because the theorem is what says they're congruent. Okay, so again, we're going to apply this to a diagram. Steps are the same. Label the diagram carefully, then write an equation, and then solve. So for this one, we have measure of angle ABC is 4x. This is ABC, I'm going to label that 4x. Measure of angle EBD now, EBD, that's this one, is 7x minus 27. What we need to do is write an equation. Think about how those two values relate to each other. What do we know about those two angles? The same measure, right? So what's the equation going to be? Yeah, 7x minus 27 equals 4x. This time the equal sign is going to go between our two values. 4x equals 7x minus 27. So with angle addition postulate, we were adding them up and equaling them to the whole thing. Linear pair postulate, we were adding them up and equaling them to 180. Vertical angles theorem says they're equal to each other. So we have to put the equal sign between them. Does that make sense? So now we're just going to solve for x here. Oopsie, how'd that happen? Subtract 4x from both sides. Actually, we could do minus 7x. You guys might like that better. Minus 7x on both sides. You get negative 3x equals negative 27. Make sure if you're going to do it that way, you keep your negative sign there. Divide by negative 3. And x is 9. What's our reason again? Vertical angles theorem. How are we going to get the measure of angle ABC? Good. Plug in x is 9 into this value. 4 times 9 then is 36 degrees. EBD, again, we plug in 9. 7 times 9 minus 27. 63 minus 27 also gives you 36 degrees. This adds another little twist here. What's the measure of angle ABE? Well, where's ABE? Here it is. What? It's not part of a given information, but you have the diagram, right? So if we know now that ABC is 36 degrees, how could we get what ABE is? Yeah. Yeah, we know that this is a straight angle. It's a linear pair. So we have to do, if this is 36, again, the diagram's not drawn to scale, but we do 180 minus 36, we should be able to get our answer here, which is what, 144? Okay, so now we're going to formally talk about what a plane is. By definition, a plane is an endless flat surface. It's two-dimensional. Endless flat surface. It has length and it has width. It does not have any depth. It's an endless flat surface. So sort of everything we're going to be doing in geometry takes place in a plane until second semester when we enter the third dimension, and then we get things that are three-dimensional like cubes and spheres and prisms and cylinders and stuff like that. But triangles and quadrilaterals and parallel lines, these are all going to be in the same plane, so an endless flat surface. If you either play football or you watch football or you like football, have you heard them talk about the plane in football? Sometimes they say, well, let's, check the replay and see if the ball crossed the plane. Did you ever hear them say that? So there's kind of like at the goal line, there's the stripe on the field, but up from that is this invisible, endless flat surface. And in order for a touchdown to be scored, the ball has to cross that plane. A player's feet don't actually have to be on the ground to score a touchdown. It just has to be the ball crosses the plane. So there could be a pile, and somebody jumps on top of the pile, and then they look from the side, and they go, well, did the ball actually cross over that invisible endless flat surface? And if the answer is yes, it's a touchdown. So that's the one situation I can think of that you might hear that word other than in this class. So the notation for plane, we have to actually use the word P-L-A-N-E, and then we need 3 letters from 3 points that are contained in that plane, but you have to use 3 non-collinear points. You can't use points that are all lined up. So this could be called, let's say, plane R, Q, V. 3 non-collinear points. And that's because if you use 3 points that are lined up with each other, like RQS, there's more than one plane that can go through that. Like I could put a plane this way going through RQS. Right? So that's not enough to define which plane you're talking about. You have to use non-collinear points. In the corner here you see this P. So that is another way to name this plane. You could just call it plane P. Usually it's a script letter. It's hard to tell with that P right there, but it's a script letter, and it's labeling not a point. So you can see that it's a letter that's not labeling a point, but it's just kind of off to the side on the plane P.